This video is about using the technique of magnetic susceptibility in order to determine the number of unpaired electrons in a solid sample. And for this video, we're going to talk about a few things. We'll determine how to use the mass susceptibility to calculate the effective magnetic moment. And then in the end, what we're going to be able to do is compare the effective magnetic moment with a theoretical spin-only magnetic moment that will allow us to determine how many unpaired electrons are present in a sample. So a little bit about magnetic susceptibility. This is a technique to measure the magnetic moment of a paramagnetic material. So background first, when we think about our definitions, we remember that a paramagnetic compound is a molecule that has unpaired electrons, and therefore will have a magnetic field that we can measure. A diamagnetic compound, by contrast, all the electrons are spin paired, and so there is no magnetic field, and so we can't use these techniques because there is no magnetic moment. The magnetic susceptibility then is the measure of the strength of interaction between a substance and the magnetic field. And then finally, we have what's known as the spin-only magnetic moment. This is a theoretical calculation, and this is what we're going to compare to our experimental value that we gathered in lab. And what this is going to do is it's going to relate the number of unpaired electrons to what the magnetic moment should be just based on the number of unpaired electrons present. Okay. So again, the key idea is we will compare our experimental magnetic moment that we will gather and then calculate to this theoretical spin-only magnetic moment to determine how many unpaired electrons are present in our sample. So first, a little bit about our magnetic susceptibility balance. This is the balance that you used in lab. It's sometimes called a Johnson-Matthey balance. Um, a simple schematic of the device can be shown here. This is what it looks like inside this box. And basically what we have is a support system, and then we have a bar going across and a spot to insert our tube. So here's your sample tube that we all used in lab. And a lot of this is supported by basically thin metal strings, which is why it's so important to be delicate with this balance, because any movement will start this swaying or bend the string, and then it won't work as well. Within our sample tube, you place your sample in the tube, and that goes in between a magnet, which is on a balance pan. And the idea of this is a paramagnetic compound will then attract the magnet in the pan and actually lift the pan off of the balance. And what we sort of record, the number that we'll see over here, has to do with how much less mass this balance is recording because of that magnetic attraction. All right. So the reading that we get from this device, our balance, we'll then use through some calculations to calculate what we call the mass susceptibility, the amount of um, the magnetic ability per gram or per unit mass of our compound. So when we ever use the magnetic balance, it's important to be careful. The balance is very fragile and costs about between $5,000 and $7,000. So we do want to be gentle with it. The other thing that's important is to make sure we record all of the data we need. So it's important that we first record the initial value of our empty tube in the balance. We need to know the mass of the sample that we put in the tube. We need to know the height of the sample that we put in the tube. We then need to record the reading of the sample within the tube, and then the temperature of the lab that day. Forgetting any of these means we can't actually continue with the calculations. So we need to make sure we have all of those. To see a demonstration of the balance and the data that you would collect, I've put together a short video that's on Canvas that you can watch of how to collect the data and get a sense of what to expect. Once we have the data, what we have to be able to do is calculate the effective magnetic moment. That's taking the raw data, that reading, and that other data, calculating the mass susceptibility, then the molar susceptibility, and then ultimately the effective magnetic moment. Again, I put together a short video on Canvas of how to go through these calculations. So for now, we'll skip that and go kind of right to the results and say, you can watch that video of how to get the calculations, but for now, we'll jump to once you get your answer and you know what the effective magnetic moment is, how can we compare that to the theoretical spin-only magnetic moment to determine how many electrons do we have? So our spin-only magnetic moment, it gets this abbreviation mu sub s for spin, and this is a fairly simple equation, and what comes out of it is mu sub s is equal to n times n plus 2 um, and the square root of that whole term, where n is the number of unpaired electrons in your sample. In the end, this gets the units Bohr magnetrons, which is symbolized by mu sub b. And if you're interested, a Bohr magnetron has the units shown here, where it's equal to the electron charge times h bar divided by 2 times the mass of an electron. But most of the time, we don't even worry about this. We'll just report our answers in Bohr magnetrons. Okay, so for example, if we want to predict the magnetic moment of our copper 2 plus, we'd have to ask ourselves how many unpaired electrons does the copper 2 plus ion have? And if we think about this, what we know is the copper D plus will be a D9 metal. And if we know that's a D9 metal, then we can only have one unpaired electron. So we can go ahead and say, with the one unpaired electron, we could plug it into our equation, and you'd get mu sub s equals the square root of 1 times 1 plus 2, which equals 1.7 Bohr magnetrons. So when we get our results in lab, what we're going to come up with is you should have a calculation of what your effective magnetic moment is. This value is what we are going to then compare to our spin-only magnetic moment. And so what we can do in the example we walked through the calculation in the other videos was looking at nickel chloride hexahydrate. And when we went through this, we can then compare the two. And what we find is you can see that going through the magnetic spin-only magnetic moment values, we can start to calculate if n equals 1, if n equals 2, if n equals 3, and so on. What would the spin-only magnetic moment be? Then with your mu effective, we can come over here and say, what did we get? And what we found from those calculations previously is our effective magnetic moment was 3.26. Again, the units are Bohr magnetrons of this. And when we compare this, we say, well, 3.26, that's somewhere in between the 2 and the 3 electrons. And we can say, in fact, we're even a little closer to the 2 unpaired electrons, and that is in fact consistent with a D8 metal, which is what we have for a nickel 2 ion. And so we should get 2 unpaired electrons. That should be what we expect. So again, what we've done in this video, hopefully, is you understand how to take your data you gathered from lab of your magnetic susceptibility of your 2 compounds that you studied and use that to determine how many unpaired electrons are present in each of those complexes.